Number one, if you checked your email this morning, you would have seen that my end of semester questionnaire email had come through. You don't necessarily need to fill that out immediately right this second, but try to get that done by sometime on Thursday. Basically saying whether you want a double or a retake is basically all you're doing. Cool on that. Okay. Today we're going to finish up talking about Chapter 3. And so double angles. Okay. And then that'll finish us lecture-wise off for the semester. Again, there's no homework assignment, there's no homework quiz, there's no test, any of that stuff associated with Chapter 6. It's just an exam-only thing. If you look inside the content library, you can find the assignments that I would have given related to Chapter 6 and their answers inside the content library. So I would suggest taking a little bit of time and at least doing the Chapter 6 test. And then the last thing, again, reminder, is that you are allowed a sheet of notes on the final exam. To use that sheet of notes, you have to turn it into me by the end of the day on December 15th. That's the Wednesday before exams start. If you'd like to use it on the exam, has to be turned in before the exams start. The 15th, yes, so a week from today. Just give you a heads up. Again, that is there mostly for your guys' specific protection, so you don't have to be the guinea pig and figure out like, oh man, you need to have this on there and this on there and this on there. And by the time 8th hour takes their exam, they're like 10 points better than you guys did because, you know what I mean? You had to go in blind. So it's there for your protection more than anything else. You're welcome. Okay. So today we're going to talk about... Or last time we talked about Chapter 6, we started this a little bit, I think on the 2nd is what my notes say. We're going to talk about the last two types of identities, the power reducing and half angle identities. Talk a little bit about solving and proofs and how those we can use these new identities to do those sorts of things, and that'll wrap us up. Cool with that plan? Okay. So we're going to talk today about the power reducing and half angle identities. So these power reducing identities allow us to take a trig functions that's squared and rewrite it as a double angle. So these are the three power reducing identities. I want to point out to you that we don't usually ever write the power reducing identity for secant, cosecant, or cotangent. How would you find them? Just the reciprocal of these ones, right? That's all it is. So we don't usually write them down because by this point it's clear. Right? Everybody's okay with that? Okay. So let's just run through a couple of examples of evaluating some angles using these power reducing identities. And then we'll do an example of a proof that we can do using this. And then we'll talk about the half angles after that. And then do a little solving at the end. Cool? Maybe I'll be specific. So if we're going to do sine squared of 3 pi over 8, we're just going to be using the power reducing for sine, which allows us to write this as 1 minus cosine of 2 times u all over 2. In this case, our u is 3 pi over 8. So far, so good? So I'm going to start by just multiplying the 2 and the 3 pi over 8. So when I do that, things just reduce and I'm end up with 3 pi over 4. Which is great, because 3 pi over 4 is a unit circle angle. So I go to my unit circle. Cosine of 3 pi over 4 is negative root 2 over 2. Oh, yeah. Yep. Sorry, I was like, oh no, this was sine problem. I'm like, no, I had cosine there. I'm dumb. So we're left with 1 plus root 2 over 2 all over 2. Do you like the way that looks? I don't. What's yucky about it? Fraction inside of a fraction, right? So let's simplify this a little bit to get it so that it's as a single fraction. So the trick here is I'm just going to multiply the top and bottom of this by 2. So I distribute the 2 in the numerator. 2 times 1 is just 2. 2 times root 2 over 2. Well, the 2's are just going to cancel and leave me with the root 2. And then the denominator, 2 times 2 is 4. That look okay to you guys? So hard as I could probably make it would be doing something like this. What if we did cotangent squared of negative 165? First issue is I go to my power reducing identities and I have no cotangent. Uh-oh. What do I do? Yeah, so really we can just say that the power reducing identity for cotangent is just the reciprocal of the power reducing identity for tangent, right? Everybody cool with that? So rather than making like super fractions, I'm just going to make it as simple as I possibly can. You know what I mean? We happy so far? Okay. Now do my multiplication. So 2 times negative 165 is negative 330. Is negative 330 a unit circle angle, though? No, all my unit circle angles are positive, right? So what do I have to do to this? We have to find something coterminal to it that is a unit circle angle. To do that, I would add 360. So far, so good. I go to my unit circle and I look up cosine of 30 degrees is root 2 over 2. I'm sorry, is root 3 over 2. Excuse me. Is that okay? Let's get rid of the fractions inside of fractions. To do that, what should I multiply the top and bottom of this by? 2, right? Whatever that denominator is. So that's going to give me 2 plus root 3 over 2 minus root 3. Do we like this answer? No, well, why not? Yeah, we got a radical in the denominator. Fiddlesticks. So, and this is actually like the worst case scenario of having a radical in the denominator because there's also addition and subtraction associated with it. So if you remember back to last year, which I'm sure you don't, the way we get rid of a radical in the denominator when there's addition or subtraction going on is by multiplying by its conjugate. So the conjugate is the same thing, it's just the different sign in the middle. So I'm going to multiply the top and bottom by 2 plus root 3. And really I would want to think about these as all having parentheses around them because we're foiling now. Everybody's okay with this? Note when I multiply root 3 times root 3, I get root 3 squared, which is the same thing as just 3. So everybody okay with the foiling that I did there? I actually wrote out the FOIL for you. Notice in the denominator, I have positive root 3 and then minus 2 root 3. Those cancel out. And then I have a 4 minus 3 down there, which is just 1. Cool. In the numerator, 4 plus 3 is 7. And 2 root 3 plus 2 root 3, we just add the coefficients, but the radical part stays the same. So that gives me 4 root 3s. So my answer is just 7 plus 4 root 3. You guys feel okay with that? It's probably as bad as that could get, one of these evaluate problems. But still not so bad, right? Not so bad. Let's do a proof here. So in this chapter, I'm going to say straight away that our usual rule of starting on the more complicated side, I'm going to throw that rule right on out the window. Because if we look at most of our identities, they're going to take something simple and make it complicated. That tends to be the route that I think is easier to go. So I look at the sine cubed. And really, I'm like, well, I don't have a good identity for sine cubed, but I do have one for sine squared. So I'm just going to think about that sine cubed as sine x times sine squared x. And I like that because I now have the sine part on both sides, right? We cool with that? With the sine squared, I can now apply my power reducing identity. Everybody's okay there? And boy, look at that. You see the divide by 2 here? That's the same thing as multiplying by 1/2, right? And now I got exactly what I need. Not so bad. Let's do one more. Okay, so I have cosine to the 4th equals 3 plus 4 times cosine 2x plus cosine 4x all over 8. Again, I'm going to start on the simple side. And I'm going to take advantage of my power reducing identity by rewriting cosine to the 4th as cosine squared times cosine squared. Now I can use my power reducing identity for cosine. And just as a little aside, how did I know that I'd want to use power reducing identities here? When I looked at the right-hand side and I saw there are coefficients on the x's, the power reducing identity is really going to be one of your best ways to go from something that has no coefficients on the x's to getting coefficients on the x's. So that was kind of my hint. Everybody cool with that? Okay. So I should go ahead and FOIL this out. I'm going to do that foiling in my head. Is that okay with everybody? Now if I look here, power reducing again, isn't it? Because of the cosine squared. Yes, of course. Sure. Is that looking okay with everybody? What should I do now? I would get rid of the fraction inside of a fraction. How is going to be the best way to do that? Yeah, we'll just multiply the top and bottom by 2. So the 2 distributes. So in the numerator, I'm going to have 2 plus 4 cosine 2x. And then the fraction, just the 2's cancel. And notice 2 times 2x is 4x. And then the last thing I have to do is just add those guys together, and we're dunzos. How's that feel? Again, they're identities or proving identities. It takes a little bit of practice. You'd probably want to run through some of them from the review or the homework. Certainly do the ones on the test to make sure you have a feel for what's going on, but it's not too dissimilar from what you're doing before. You just have more tools to work with now, right? But the same kind of approaches are still going to be the approach that you'd want to use. So next we're going to talk about these half angle identities. Oops, plus or minus. And then the tangent one actually has 3 separate versions that you can use depending on what you want to do. So let's say that I want to do cosine of 75. Notice that 75 is not a unit circle angle. So what I'm going to do is I'm going to start by rewriting 75 as something divided by 2. What divided by 2 is 75? 150. Everybody's okay with that? Notice that 150 is a unit circle identity. So applying my half angle identity, again, notice that my u in this case is just the 150, not 150 over 2. I get this. Let's sort out right this moment whether we should have a plus or minus here. So if I go back and I look at my original problem, 75, we're doing cosine of 75 degrees, correct? What quadrant is 75 degrees in? Quadrant 1, 2, 3, 4. For a standard position angle? Quadrant 1, right? In quadrant 1, cosine is positive, negative, positive. So in this case, we want the plus. Everybody okay with that? The thing you have to remember here is that determining whether it's positive or negative, we have to look at the very beginning value, not the 150 that we turn it to 75 into 150 over 2. We have to look all the way back to the very beginning original problem. But that's not difficult, right? You have to remember to do it, but it's not difficult to do that. So if I do cosine of 150, cosine of 150 degrees is negative root 3 over 2. That's a unit circle value. I could probably do a better job of writing that. Let's write it vertically. Everybody's good here? Do we like the way that answer looks? What's wrong with it? And I got fractions inside of fractions, right? Let's take care of that. What should I multiply the top and bottom of this by to get rid of the fraction inside of fractions? Close. Yeah, it's actually going to be square root 2 over 2. To multiply that 2 inside the radical, the 2 also has to be under a radical. So Yes, it matters.
Like if the do chew and then leave the square root there.
Uh-huh. I can't grade what you mean. I can only grade what you write. You know what I mean? It'd be like saying 2 times root 2 is root 4. Right? Like you can't, that's wrong. That's wrong. You know, like everybody's happy with what we did there though? This can simplify though a little bit, because remember the radical of a fraction is the same as the radical of the numerator divided by the radical of the denominator. And root 4 is just 2. Everybody happy? And that's as good as we can do. I want to point out too that just to be careful about how you're drawing your radicals. Make sure that it's really clear that if the radical is over the entire fraction or if it's over just the numerator. Some of us can get a little bit messy with that, and that matters a lot in this case, which one you've drawn. You guys see the difference there? One of them, the radical's over the entire fraction. One of them, the radical's only in the numerator. Just be careful with that when you're drawing. Again, I have to go with what you've written, not necessarily what you mean. Okay. Let's do one more. Let's say we're going to do tan of negative 105. First thing I want to do is rewrite this as a half angle. So negative 105 is the same thing as what divided by 2? Oh, come on, guys. Negative 210, right? Okay. Now remember that half angle identities for tangent, there were 3 of them. Let's go back and look at them, right? There are 3 there listed. Which one would be the one that is going to be the easiest for us to deal with? Do you want the one with the radical and the plus and minus? No. Which one do you want between 1 minus cosine u over sine u and sine u over 1 plus cosine u? Which one's going to be the easier one to deal with? Why? Why would I want the one with the sine u in the denominator? Here's what I'll tell you. Is if I have to rationalize my denominator, which could very well have to happen, I'd much rather have no addition and subtraction in the denominator so I don't have to do any foiling and multiplying by conjugates. I can just like straight multiply by root 2 or root 3 or something and just be done with it. So again, any of them will work. It's a question of how much of an appetite do you have for simplifying. I'm going to spend a little bit more time in the beginning thinking about what's going to make my life easiest. I don't mind spending energy to be lazy. You know what I mean? Okay. So we're going to have 1 minus cosine of negative 210 over sine negative 210. Now, is negative 210 a unit circle angle? No. Can we convert it to a unit circle angle? How do we do that? Add 360. When I add 360 to this, I get 150. Cool. Okay. So now I'll just go to my unit circle. Cosine of 150 is negative root 3 over 2. And sine of negative 150 is, or I'm sorry, a positive 150 is 1/2. Well, that's nice. I don't even have a radical in the denominator, so that's cool. Notice that if we had done the other way, though, we would have, right? So get rid of the fractions. And I'm just left with 2 plus root 3 It's over 1, but I'm not going to bother even writing the over 1 for you guys. And we're done. It's not so bad, right? Okay. Let's do a proof involving these identities real quick. Yes, of course. All right. So when I look at this, this is the piece that I'm interested in because I see the half angle in it. On the other side, I see no half angles. So I'm going to use one of the half angle identities. So the half angle identity, I have only one choice. So I have plus or minus root 1 plus cosine x over 2. And then notice that this is a half angle squared. So when I put the identity on there, I still have that squared on the outside, which is just freaking awesome. You know why? Because that squared is going to nix the plus or minus, because if I'm squaring something, whether it was positive or negative, when I square it, positive, and it's going to cancel the root. Yeah, buddy. That's what I'm talking about. Then looky here. Times 2 divides by 2. Yada here. So we just got to distribute this stuff through. And I know cosine x times secant x is just 1, right? I skipped some steps on doing that, but at this point, I expect that you look at that and you're like, yeah, I can. That's easy to show that that's 1. You know, you guys did good on the homework quizzes. I didn't see most of you take a chapter 5 test, but I think if you would have had to do it, you would have done pretty well. It wasn't that bad. The proofs people did better on than the first page. Okay. Feel okay? All right. So one last topic I want to talk about here is just solving. So let's say that we want to solve 2x is equal to sine x. And let's just do, you know, on this interval 0 to 2 pi or whatever. Now remember, when we did this last time, when we had a coefficient of 2, that made life kind of a pain in the butt, right? This time, what we're going to do is we're going to use our double angle identities so that we don't have to deal with having to worry about like finding the infinite solution and then doing the division and blah, 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 doing it. We don't have to do any of that stuff if we're using an identity and knocking everything down to x's. We can just treat it like a straight unit circle problem. Okay with that plan? The hitch on this one, though, is that if I look at my double angle identity for cosine, there's actually 3 versions of this. Let's just go to this. Right? Which one would be the one that I want to choose? There is a correct answer here. The last one. Very good. Why? Yeah, if I look at the problem I had, if I use that one, I'm only going to have signs left in my problem, which makes factoring and getting like one trig function way more realistic than the other one, than otherwise. Does that make sense? So if I can make a single trig function, that's the version of the identity I'd want to choose, is the one that gets me a single trig function. Okay, so I'm going to just get everything onto one side. So I'm going to add the sign squared over and then subtract the 1 over. Everybody's okay with that? I put it onto the right-hand side so the coefficient on the leading coefficient would be positive, because it makes the factoring now simple.
Isn't it 1 minus 2 sine squared?
Oh, yes. Thank you. Good point, John. Okay, there we go. So there's my factoring problem. So I need to find two things that multiply to give me 2 times -1. And then add to give me 1. I mean, if you guys can't figure out 2 and -1 on that, I don't know what to tell you. So I use those two numbers to replace the middle term, or break it apart into 2 pieces, and then make 2 groups. From the first group, I can take out a leading or a greatest common factor of 2 sine x, leaving you with a sine x plus 1. From the second group, I can take out a -1, leaving you with sine x plus 1. Since each of them contains a sine x plus 1, I can take that out, and I'm left with 2 sine x minus 1. And then I can set each of these equal to 0 and solve. So here x is going to equal sine inverse of -1. When I go to my unit circle, that occurs only at 3 pi over 2. And here I get x is equal to sine inverse of 1/2. When I go to my unit circle, that happens at pi over 3 and 2 pi over 3. And we're done. The nice part about this was I didn't have to ever divide by 2, right? When I was solving for x in the previous chapter, when we had to solve by 2, it kind of threw a monkey wrench in the whole thing, and we had to find the infinite solution first and then divide by the 2 over, and it changed what the coterminals were, and it had to then regenerate our unit circle answer. Here, because I used the identity, it made the solving a little bit more difficult. But when I actually did the inverse, it was completely straightforward. It was just looking from the values on the unit circle. So that's your trade-off. Me, I prefer the oh my goodness, guys. This is that's for cosine of 1/2. This should be pi over 6 and 5 pi over 6, excuse me. Yes. Of course. Sure. Let's do another one of these. Sound good to you guys? Let's do sine 2x equals -2 cosine squared x. And let's get crazy here. and go from negative 4 pi to negative 2 pi. So I would start by using my double angle formula to get rid of the sine 2x. If I go and I look at my identity, sine 2x is 2 times sine x times cosine x. And I'm going to move everything onto one side, so I'm going to add the 2 cosine squared x over. But he's good. I notice I have a greatest common factor of 2 cosine x. So I'm going to factor that off. Is that okay? I'm going to then set each of these factors equal to 0. So 2 cos x equals 0. Divide by 2. Doesn't do anything. So cosine inverse of 0. Ugh, come on, Ben. Happens at 0 and at pi. And then we'll subtract 2 pi from those. I get negative 2 pi and negative pi. Those are too big still. So I'll just subtract another 2 pi. And I get negative 4 pi and negative 3 pi. Those fall inside of my interval. Everybody's okay with that? The other piece, this is a little bit tricky. I'm going to subtract the sine x over. And then divide by cosine x. Notice that I haven't canceled the cosines completely, right? There's still a cosine in the denominator. That's why it's okay to divide by the variable. It's because the variable doesn't really ever go away. We just moved it. Notice that sine over cosine is tangent. And then I'm going to move the negative sign back over here, just multiplying by the negative. So then I'm going to go to the unit circle and pull the places where cosine inverse is negative 1. That happens at 3 pi over 4 and also at 7 pi over 4. And then if we subtract, I know from the previous one that I had to subtract 2 pi twice. So that's why I'm cutting to the chase here and just doing 4 pi. Is that okay? Okay. So 4 pi is the same thing as 16 pi over 4, so that's going to be negative 13 pi over 4, and then negative 9 pi over 4. Ah! Look at your dumb teacher did it again. Cosine is 0 at pi over 2 and 3 pi over 2. Gee willikers. My apologies. Confound it. Okay, and that wraps up chapter 6 for us.